This is our last of the resonance unit 4, but it has a couple of chapters, actually more than that, being referred to. The thing that I want to talk about first is really quite spectacular, and it has to do with two kinds of resonance, but in particular, since we've already done the linear additive resonance, we're going to take up the multiplicative one, which is obviously non-linear. The common name for this is parametric resonance, which means you're resonating a parameter like a spring constant, as opposed to some amplitude of a force. That's what was talked about in the first chapter of this Unit 4. Then we're going to look at something that's relevant to the trebuchet. The trebuchet makes use of this parametric resonance, and that's another way to understand how it gets its throw, its incredible energy. And then we're going to make an analogy between parametric resonance dynamics and just the plain old quantum mechanical Schrodinger equation, and we'll show how electronic band theory has an analogous classical mechanics that goes with it. That's really a mind blower, so we'll have some fun with that, and we have a lot of animations to show what's going on. And then what I'd like to do is take on resonance of 2 bodies, 3 bodies, 4 bodies, but first 2 bodies, just to make connection with a symmetry method. Group theory it's called. Applications of group representation theory is the full name. And we'll look at a C2 symmetric, and then C3, C4, and so on. And this is a spectacularly beautiful way to learn about Fourier analysis. So by the time we get most of the way through this, you'll see what I'm talking about with regard to that. And then if we have time, we're going to come back and look at some of the resonances that are associated with Cn, where n is quite large, and give rise to the almost, I guess, called chaotic, but it's not really chaotic, it's very ordered, it just looks chaotic. Things that are described by the mathematics of Ferry sums and Ford circles. So this is a tall order, so let's get started. And this is the first idea of 2 kinds of resonance. The one that we talked about in the first chapter of Unit 4 was supposedly an electric field. That's the most common application of it. It's going on while we're looking at the screen right now in our eyes and in the production of the light that comes down here onto me. But anyway, oscillator here leaving out the damping, and that's the force damped harmonic oscillator without the damping right here, and there's the force sitting there as a linear term on the inhomogeneous placement side of the equation. Then you take something like this and stick it right into the equation of the oscillator, and this then is the spring constant that's an explicit function of time. So that's what we're going to talk about today. It's called parametric resonance simply because the parameter is being wiggled. But the idea, of course, is that really is, if you just use replace the independent variable here with time. I mean, that's what's happened to the Schrodinger equation, is the distance, spatial part of the spatial independent variable of Schrodinger equation has been replaced with time. That's what makes it a little hard to think about this. So we're going to spend a lot of time making the connection with that. And the idea that that's being stimulated. And what we're going to use, and this is something I didn't notice until, well, just a few years ago, is when people talk about parametric resonance, they always used to use the analogy of a child on a swing pulling on the rope and getting it going. That's really complicated, as it turns out. It's a horrible equation. this is much easier. You just have a pendulum here, and instead of going like this to resonate it, that's this stuff, you go like this. That's the parametric analysis. Basically what you're doing is you're wiggling gravity. Think of yourself on an Einstein elevator that's jerky, right? So that's what we'll work with. That's the thing we'll study. And as I said, the X-stimulant one looks like this. And what you're doing is you're applying, is you're imagining you're putting some artificial gravity in the X direction on your pendulum. And so for small oscillations, this is the equation of motion. But if instead, while you're doing this, you stop doing this and start doing this, then you're really talking about a nonlinear resonance, because now the gravity part here has an additional term, accelerative term to it. So this is essentially the Schrodinger equation. We have to marry those two to pull off what we're doing here. But the really nasty equation, which is the one that the trebuchet really obeys, and this is including gravity, would be these two combined with a sine and a cosine driving it. Now, the thing that we're doing here is we're going to assume that the angle is pretty small. When it is small, then this analogy between the vertically jerked pendulum and a Schrodinger equation is good. But the sine Schrodinger equation is needed if the angle gets you know, more than say 5 or 10 degrees. Anyway, we'll play with the simulations to see what this all means. But this I call this the nasty equation, because it's really a difficult, very nonlinear equation with lots of weird amplification going on. Now, this is Arkansas, so I should point out to you, if you've ever seen these things, and I think I've seen them with a picture of a hog on them being sold at roadside attractions, or go out to the country and by Beaver Dam, I think is where I saw it in a store, bait shop. And it's just a nail, a very skinny nail, holding a propeller blade, and then somebody's cut a bunch of notches in a piece of wood, and then you get a hard piece of wood to rub this thing, you go like that, and if you just put your finger on this thing, hold it in one direction, and make sure the vibrations are in the vertical direction, this thing will parametrically amplify. That is, this blade will also start to spin. Have you ever seen one of these things? Yeah, I've been looking for them too ever since I started this. Anyway, we have been hoping to go ahead and build actually a device that would do both. This one would be the one that would be positioned for nonlinear resonance, vertically jerk the fulcrum, but you could try it at different angles and study the nasty equation. Anyway, these are one of many things that we're hopeful about getting going here.
Basically, control optimization.
My procrastination.
Goal of flipping it over the top with minimal fluence, minimal energy. There's a lot going on there.
So here's the algebraic part. Idea is to take good old Schrodinger's equation, which is an equation in X, of course, with a potential and an energy eigenvalue for that differential equation, and replace the X with time. That's our vertically jerked pendulum equation right there. So where here we have a potential, if you're thinking about a crystal field, you'd be thinking about the Matthew equation, where you have a cosine to represent the lattice potential. Okay, so this is a good start for discussing what our next topic is going to be, and that is the waves in periodic structure, periodic potential being this example. Here, we've got an accelerative, acceleration literally, that's got a coefficient involving the frequency squared of this thing. This is an acceleration, so whatever I'm doing in motion, I have to take the second derivative of this, and that gives me an omega squared for my cosine. So that's what actually sits right here, multiplying the inverse pendulum length. Okay. So that's our periodic roller coaster, you might say, there, if it was just time. And this is time, so independent variable being t is what we're dealing with. So what we're going to do is try to match this. This is the, when I said Matthew equation, I meant the French Matthew. Probably not pronouncing it quite right. But in any case, we're going to take this thing right here and marry it to this. So this little coefficient right here is going to be that. And so forth. The energy is going to be this pendulum parameter, G over L. And also the independent variable has to be taken care of. This one, just plain old nx to get me n oscillations per radian. And this right here, having an omega y, that's the how fast I'm moving up and down. I'm holding this pendulum. So connection relations, first of all, there's a differential relation. And then what I need to really connect the dt and the dx is this relation right here, which we can put together. Now, what we're going to do, it turns out, you'll see this in a minute, is we're going to be producing with either one of these equations a series of bands of allowed energies. And that's what you speak of when you speak of this band theory for a crystal, this one-dimensional crystal here. And then there'll be gaps in those bands. And if you let this number n here be equal to 2, the result of solving either one of these equations, and they'll be the same if we can make these connections, is to get the edges of the bands. In other words, actually get a picture of the boundaries of the bands. Then the solutions that lie inside the band can be discussed more easily once you know what the boundaries are in energy, in terms of energy as a function of the parameters of either one of these things. So there's the QM energy E right here, and that is being connected to G over L. And then, let's see, we've already got a connection here that we've put together. And what happens to this thing right here, this guy right here being connected to the, let's see if I've got that right, AY n squared. Well, using the energy relation right here to make the same units as the potential has this relation. So this is the QM potential being related to the amplitude of our amplitude of the wiggle, but now I've replaced the time thing with x. So what we're doing is taking a problem that most of us are grown up doing some band theory. I'm replacing this new equation right here with the band equation, now Schrodinger's equation in the band. And what happens at this point is that this particular frequency drops out from that relationship, but it's still in the eigenvalue a part of it. Okay, now let's see. We're going to take the string length, the pendulum length, to be 1, just to make the things simpler. And as I said, n equal 2 is a good thing to have. So that n squared thing here becomes 4, and that relates our potential height, the barrier height of the actual potential is 4 times the amplitude here. Okay, now the screwy thing is this. The connection between the thing that has frequency over here and actually disappears from the equation, at least when you write it in this form, but the connection between the eigenvalue and this parameter right here, the actual energy and this parameter is inverse squared. Okay, that's kind of weird. We'll deal with that when we get to it. So what we're going to do is look at the comparison between Schrodinger equation written in space and then this pendulum thing here without the stimulus, okay, at first. They're both exponential solutions, that is, sine and cosine solutions, but we're doing it complex amplitudes in both cases here. So the energy is just k squared. Here the frequency is just square root of J over L, G over L, gravity over L. And we're going to have some boundary conditions to make the thing a tractable solution. So it's very obvious I need boundary conditions for a band. Presumably the band would be in some kind of box. So I'd have a certain length that I would ask this thing to fit the waves to. And demanding this be 1, it makes you have a k value, 2 pi times integer. So you just put more and more waves inside that box. Here we're going to demand that whatever we get repeats perfectly after a certain time t. So there's going to be a time boundary on this one that's analogous to this one. So that's the idea, is that this angle here that's going to be whipping about comes back to your initial value after a certain time. So that's going to make whenever you put wavy equations in boxes, what you get is quantization. So that's basically this quantization we're all familiar with. We're also going to have quantization of frequency here. And that's going to allow us to solve this equation by matrix diagonalization. And we don't have to do the whole matrix because it's infinitely large, but you get a very good solution by just considering sub-matrices, sometimes 2, 3, 4, 5 dimensions is all that's necessary. And you get a quite accurate solution to this. The analytic solutions for getting this are really terrible, and they're also terrible in their conversions. So most people avoid them. There's a big section in Morse and Feshbach about it, but what you discover after you've read all that stuff and played with it, it really is quite useful, especially when we have a calculator or computer that can diagonalize small matrices quickly. So anyway, the idea here is that we're going to have a differential operator, which is the second derivative, and then a potential operator. Well, potential operator is just going to be coordinate, a function of x, and we're going to be interested in the Fourier representation of that, and that's fairly easy to find, especially when you've got a cosine, because it's just a Fourier component, number, whatever, n. So this is the matrix eigenvalue equation that we'll be looking to solve. And we'll have a similar one over here, but this is just a continuation of, this is the potential here, this is the potential. And this will work for anything that is reasonably like a cosine, that is not having no singularities. This is just for the cosine, and when you do that, you're going to get 0 unless the k is k plus n, whatever this n is, and we're going to take 2 for that. Whenever that is equal to, or the j is going to be equal to that, or equal to K minus n. So there are going to be two possibilities. So I'm going to run the other screen here ahead to this point so that we can look at the matrix that comes out and compare it to some other things. So there's the thing. The whole thing just moved up so I can actually put the matrices on the screen right here. So with the values that we've taken here, I will have two possible solutions, even and odd. And the eigenvalues that we're talking about for a double derivative are just squares of integers, either the even integers or the odd integers. And then this off-diagonal thing right here, this little v, that is, as we showed before, the v0 over 2 is of interest here, and that's related to 4 times the acceleration coefficient divided by the length of the pendulum times 2. So we're talking about 2 times the acceleration coefficient over the length of the pendulum. And we're going to take that to be 1, so it's just 2 times ay. That's the coefficient of the acceleration for that. It's related to our potential just by a factor there of 4 we talked about before. Okay, so go ahead and take this thing to that point. And then here are some examples of eigenvalues that you get for this. Now, it's really very amplitude dependent. As I increase the amplitude of the oscillations of a potential, I get very different solutions than I had before I changed that. So I consider here a case of V0 equal 0.2, and here are the eigenvalues that you get for the 0, the plus or minus 1, plus or minus 2, and plus or minus 3. Now, what those eigenvalues are some things that are very close to 1 squared. Let's see, this is the energy. Okay, so talking about this energy being 1, and then here 2 squared is 4. Okay, so this is very close to 4. Okay, this is a small perturbation here. So these two eigenvalues are nearly degenerate. Degenerate is being broken by the symmetry breaking here. Then here's 3. 3 squared is 9. You can see to 4 figures, or 3 figures, it's still 9. Okay? But then as you go with a higher potential, then they split noticeably. This one is showing up here with about 5% splitting. And this one has got more than that. And then the 2, 1 eigenvalues, they split almost immediately and go in fact linearly. There's a reason for that. And then this guy right here, the ground state, which starts at 0 but now starts to rise or drop. Actually, it's dropping. Now, one of the points that I want to make here, and this is the thing that's peculiar about this, is there are 2 limits that we're talking about. First of all, phi is very small, then sine of phi is equal to phi, and so the equation that we're talking about, which has a sine phi in it, and you have that replaced by phi. There's also the possibility of a pendulum being in the inverted position. That is, at its highest point, where phi is very nearly equal to pi, it's oscillations around that that are peculiar and quite wonderful. So we'll be seeing examples of that. At that point, the cosine is close to -1, and the sine is close to pi minus, and now the phi that we're talking about here will be the deviation from the top. So we're really looking at 2 classes of solutions, those that are inverted, and these are marked right here. If you have a minus here, you're inverted. And we'll draw a graph of this so you can see how that works. In any case, each eigenvalue here, whichever that the value of this is, it then implies that the frequency of the wiggle that corresponds to it. Remember, this is the thing is sort of being quantized, but in an inverse sort of way here. That value is being given here. So it's always 2 over the square root of the eigenvalue from our connection formula. And this is the inverse square that I was talking about before. That's so weird. In any case, this is for 0.2 and 2.0 amplitude. So a very small perturbation and then a fairly sizable one is being shown here. And here are the actual frequencies that we're going to set on a simulation of the pendulum, the inverted pendulum, that will be in these, will show what's happening. So let's take a look at some of those. What I'm going to do, I think, is run the simulations over there and look at the table of them, the graph of them here. So what we're plotting here in this direction is something proportional to the acceleration. How much are you jerking this pendulum? How big is that arrow right there? And then the frequency that you're jerking it, that's related to the inverse square root of the eigenvalues. The eigenvalues are shown by these red, pick a particular value of the crystal amplitude, a particular value of it, and then look, here's an enormous gap from here to here, where the wave function solution would blow up and not give you anything that was useful. Here is a very narrow band at this particular value of the amplitude, and we'll look at some of those. That's also below the 0 point numbers. This is one that's associated with the negative eigenvalue. If it's a negative eigenvalue, it's an inverted pendulum, and just in this narrow region of the parameters, it's stable. So we're going to be looking at some classical mechanics of how you ride a unicycle. In other words, how do you stay up on a wheel, right? And most of the time, if you've ever tried it, you don't. You fall down and probably end up in the emergency room. But, so you're talking about a very dangerous toy there. But up here, you see, it's all just hanging. And the question is, will this jerking up and down cause it to go exponential, to trebuchet? And that's what happens from here, between these two, from here to there at this particular amplitude. Now, as you close in on the thing, you see here's this linear splitting that you get simply because a wave function with 1 couples to that cosine very easily. So there's this linear splitting right here, but all of the other splittings in band theory for this Matthew or cosine crystal field are very high order. In other words, it doesn't split at all practically up there at that eigenvalue. But for these 2 plus and 2 minus, they start to show an open mouth there. But it's second or higher order splitting. This is first order right here. And it goes with this part of this band right here. It simply sinks immediately, almost in a quadratic fashion. But this one follows it, eventually making a very narrow band down there, huge gap, and then a medium-sized band right here with a much smaller gap. And then as you get up here, the gap is even less. So that's what we're really talking about. And this marking of the band is connecting to this line right here, actually. This is what we're talking about, near 2 value for V0. Okay? V0 equal 2, and the energy is, well, that one is minus 0.44 according to the values that we have in these tables right here. You see the E0 up there, right about there. That's minus 0.451. And then the next one right here, so between here and here, I've got a minus 0.1 there. That's just about right there. So this is about 0.44, and that's almost 0 there. Very small compared to that. Let's see if that shows right there. That's for V equal to 0. Here, back here at 0.2, that would be back here someplace. There's just a very small region that's minus, and the other one is positive. Okay, almost all of the energies are positive here, but now we get this little region here that I call unicycle region, where you're trying to be stable on upside down pendulum. Okay, let's take this over here. Let's see if these are some of the formulas that are simplified for this particular case, replacing energy to the jerk frequency of the classical problem. Okay, here are some examples of wave functions. That's what we want to simulate. So first one I probably ought to show is just what happens when you start off inverted or anything in this region here. Down in the lower regions, it's really very easy to have anything below this thing practically is going to be unstable. So I will, I guess, we could take our choice here which computer we want to have it do the work for us. Let's try this one over here, and then we can come back. I just want to see this one first. So let's take a look at that. So there's a pendulum that was down, but it's not going to stay down. Look at the wave function. It's already trebuchet. Okay, so there's the usual unstable motion that you get in these kind of gaps. Okay, so there's no chance to make an eigenfunction out of something that goes fast. Now remember, we're talking about something as sine phi. The Schrodinger equation is talking about phi. So the Schrodinger equation analogy breaks down. I think the equation, quantum mechanical equation that goes with the Schrodinger equation is called the sine-Gordon equation, a sort of a joke on the Klein-Gordon equation. Okay, so it's an equation in which the wave function is replaced by a sinusoidal function. And if that's the case, then we are doing that here. So that's another item that's true about this. Okay, now let's take a look. I think the first one that I'd like to show you is one that's at the bottom here. This is, this is talking about an amplitude of 0.5 in this particular one. That gives you I think this is the 1 minus mode, and then this is the 0 plus mode. Let's look at this one first. This one is quite beautiful, and I will try to get it going over here. So let me take this one back to the lecture, and we'll start it up right here. This is this one right here. This is lower energy. So there's a typical wave function. Now wave function can be normalized differently. If I move this thing in here a little bit to start it, it just does the same thing. If I move it out a ways, almost does the same thing, but I think you see that something's happening. So this is the breakdown of the sine phi equal phi. This is going to blow up. Now it's trebucheting, right? Okay. So somewhere in this region, right about here, I can start the thing up and maybe not blow up, at least not for a while. That one obviously is on its way too, right? So these solutions, this one probably is the closest to one that would stay pretty much on the screen till it got off the screen to the right. And you can see eventually it's going to blow up too. Okay, so, and we can start on the other side too. You see the thing curving down every time it gets into a barrier there. And it's going to blow up going the other way if we waited a long time. Okay? So these are all fair solutions to the ones that are at least small amplitude are pretty good solutions to the Matthew equation for a wave function that is feeling the cosine potential that's drawn in the light blue there. Okay? So let's pause this one. Now let's look at one that's just a little bit higher. So the other side of the band, that's this one right here. I'll go back to the lecture, back to the lecture, and do the stimulation that goes with this. So this is the other side of the band, you see. These are things that are on the Brisson zone boundary of the lattice, if you were to think of this as a lattice. And it is actually quite stable. I can take it out to about here and have it stay in the neighborhood up pretty nicely. And of course I can start from either side. If I start here, I'm starting on the downside, you see. That's, you know, if you have a wave function that's an eigenfunction, then minus that is also. But you can see that the unicyclist, this is what a unicyclist I think would look for. This is one where there's a lot of leeway. If you keep the amplitude and keep the frequency, you're going to be able to be inverted stably. You've made yourself a little quasi-potential well that has a pretty good extent to it, you see. I can come probably way over here and maybe stick around for a while before it starts to go wild. But even when it, you know, goes wild, it's just a question of, you know, hanging on. You have to hang on to that amplitude and you have to hang on to that frequency. And you're inverted and stay, you know, reasonably stable. That's really, you know, quite cool, I think. So
non-intuitive.
the other solutions that this thing has, let me pause this one and come back. The other solutions that are higher up are all upside. I mean, where a pendulum usually would like to be. This is the 1+ mode. And it's kind of neat. It gets real flat inside the barrier there, okay? And then cranks across inside the well. So that's this thing right here. A little bit like this one, except it's just on the next band. It's up here. The 1 plus B2 is the way it's described. It means bilaterally symmetric, but at each well anti-symmetric. And you can see it's plus and minus inside the well. It's hanging onto the sides pretty well. And then let's pause this one. Go look at next one up from here. This guy right here. This is the 2 minus A2. And again, I can probably give that a little bit more amplitude and still have it survive.
actually does spread out a good deal.
There you go, right there.
You can let it run for a while.
But it is feeling the difference between a sine of phi and phi, and so it's going to be stable. It's not going to take off and go inverted, but it's going to draw a funny kind of Lissajous pattern. So the exact solution for the pendulum is, by this time, very different from its analog. So that's kind of neat for that one. But basically, for a while, if you draw this thing with bigger scale, it behaves like a wave function. And then the last one we'll take a look at here. Let me go ahead and bring this guy to pause here before I do look at this last one. This guy right here, the 2 plus A mode. That's this guy. It's kind of neat. And again, I can probably crank up the amplitude to start this thing. Not to say maybe that much. And it's not too bad. But you can see it's starting to make another one of those Lissajous, quasi-Lissajous patterns. Anyway, this is, I think, one of the more beautiful examples of really, I mean, these are group theoretical notations, and we'll talk a little bit about those for our coupled oscillators and bands, so band theory for that. But this is really deserves a lot of thought and study. It's got some really neat things about it that people just didn't look at that much because the calculations of the thing do involve a diagonalization and then some more work to actually simulate the wave functions. Okay. Now, the bands that you get for square, well, in other words, if you were to take your pendulum and go jerk, 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 make it a square motion in time, okay, they're quite interesting themselves. They don't hang down like an oscillator does because the potential's all up. You can't go in, can't go below there very far. These bands behave pretty nicely until you get up in high regions, or else you make this thing a little bit wider here, and you start seeing crossing of bands. That also is an interesting thing for the classical thing. These are examples of the solutions that lie inside those bands. Here's opening up, so that's a gap. That would cause a thing to explode. But in here, it would be, well, you know, it would not explode. It would be a wave function that would be acceptable for quantum mechanics. That's a big gap that's opening. There's a huge gap right in there. Here's a band that's closing. You really have to be careful in order to get your energies right so they don't blow up. Gives you a feeling for what it means to find an eigenfunction of a potential that is extensive. And this one is just a square. Well, these things are all available. They're part of the quantum mechanics, unit 5 in chapter 14 of that book, just sitting over there in the corner. Okay, now let's come back to Earth a little bit here and recall our two-dimensional oscillator, the potential, and this time this is the bilaterally symmetric one, and here are the two spinners, if you will, the unit one. It's usually called sigma 0, and then sigma bilaterally or balanced symmetry. Okay, And the idea is that the classical thing for this is a square. So what we're looking at for a K matrix in a B-type system, bilaterally balanced system, is the square of this matrix. That's this thing. But it still has the same basic symmetry form. It's a number times the sigma 0 unit operator, and then in some other number parameters times the sigma b. And the idea is that the matrices mirror the actual multiplication table for the symmetry in question here, the bilateral symmetry. This is a group that's called cyclic 2. That is, you have an operator, you square it and you get 1, and then you square it again, or multiply it again, cube it, and you get the operator and so forth. So it's back and forth. You're talking about a binary system. You're talking about a system of a classical computer, which has just bits 1 and 0. And we're going to use that notation, the Boolean notation, to characterize the symmetry representations that are responsible for keeping track of the symmetry that these eigenfunctions have. But the whole idea is that if, in fact, your Hamiltonian is represented by a linear combination of group operators, and group operators obey a simple enough multiplication structure, you have a way to find the eigenfunctions just from symmetry ideas. And this is, as I say, the simplest, I would say non-trivial, but it would be called trivial after you get used to this stuff. Because we've already seen that the two solutions to this thing are symmetric modes and anti-symmetric modes. So that's you know, what we found before when we did this problem, just the old-fashioned way. But let's just go ahead here, so we've never seen it before, and use the notation 0 and 1 for the two settings of my bits here. First setting is to make this one go out and be a unit distance from its equilibrium position, but leave that one in its equilibrium position. And then the reverse. That is, this state multiplied by a reflection operator through the middle, okay? And that means I'm going to be moving this, actually I would think of it as a turnover operation, really, because otherwise I would have taken this thing and reflected it and had this one move in and that one back in its position. That's a little bit of a problem with this kind of symmetry, because there are more ways to express how you go with a C2. You can have a C2 that's a reflection, or you can have one that's a rotation by 180, just for this system. Or you could just have one that just permutes them, and that's kind of what we've got here. So those are your two base states, 0 and 1. Call them X and Y, or another way to designate it was by numbers modulo 2. This is any even number. This is any odd number, including -1 or 3. The notation is, at this point, making this look harder than it really is, so we'll wait to say more about that. In any case, once you have a multiplication table like this, it's pretty easy to turn that multiplication table into a Hamilton-Cayley equation. That is an equation that involves powers of the operators, including the 0th power, being equal to 0. And once you have that, then you have a product of two unnormalized projectors, the things that we called little p when we did the eigenvalue business, okay? So we have an equation p plus 1 and p minus 1 equals 0. And that's an orthogonality equation. If we go ahead and take the eigenvalues with their differences, then you get a 2 in the denominator here. 1 minus a -1 is 2. and similar for this one. So you get 1 plus sigma and 1 minus sigma as projection operators for your solution. So when you apply a projection operator from the symmetry to this system, you'll produce either a plus eigenfunction or a minus eigenfunction. That's the whole idea of group representation theory in quantum mechanics or classical mechanics. And it's the beginning of Fourier analysis of just two things. So applying those projection operators would either give you this, where the thing is just translating, or this thing, where they're translating against each other. Even and odd is what you would probably call that. But those A's and B's that we saw before, those A's and B's are even for A, odd for B. That's just a tradition that unfortunately we live with because people that did this didn't see the whole picture when it first emerged. So anyway, there's a lot of ways to write the eigenstate plus and the eigenstate minus. And I see an error right here. This one is 0 mod 2, this one should be 1 mod 2, and it's associated with the odd or minus symmetry. Okay, now in group theory, all of groups have a character table. And all the finite groups will have a character table, and some of the infinite ones will also have them that will become a formula. The idea is, I like to do phasors, so I apply a phasor to these oscillators, I designate them. There's a symmetric phasor where the phasors are going together, and here, this one, they're going out of phase and in phase. This one's both are in phase, and these are out of phase. Well, of course, if you look this group up at the top of the listing of character tables, we wouldn't have most of the notation we have here, but you would see a table with 1, 1, and then 1 minus 1. This would be the A mode, this would be the B mode. And that notation has, taken over over many years. We're just trying to make a change to that, and you'll see why in a minute here. But what we have here are what I call the P numbers. That's for a position point, and their numbers modulo 2. And the same thing for the M. The M is a magnetic quantum number, or momentum, or wave number, or something. M is a very common letter used to describe Zeeman states that come out with certain quanta of angular momentum. So we'll use P's for the top of the character table and M's for the side. This will make more sense later on. But that is where we're headed. We're trying to connect some rather abstract mathematics with the physics here. So we'll go on and do a 3 pronged or massed oscillator. And here we're assuming the masses are all equal and that they are located in a geometrical way such that a triangular symmetry is present. And what you do is you look at the symmetry product table first, and notice that I have some operator here to the 0th power, to the 1st power, to the 2nd power. That's the other reason for using the letter P to designate the column heads of a table that we'll be making shortly, the character table. And then the idea is that the product of, well, this with itself is just 1, but this with that, that's the unit operator there. It gives me R1 and R2. Squared R, and R to the 1st power. And then here they are again, but this is a weird kind of group table that puts the inverse operators in the left-hand side of the table. The reason for that is so that I get the 1s all down the diagonal. And then to figure out what matrix will represent each of these operators as a Hamiltonian, actually, but the actual matrix representations are just shown for R1 as the place where R, the first power, resides in the table. That's here, here, and here. So I've got a 1, 1, and 1. And then R squared, okay, it has a coefficient R2. That coefficient R2 multiplies the matrix that has R squared located with a 1 in the actual matrix. So here is an example of a slightly less trivial Hamiltonian in which it's a linear combination with 3 coefficients, one for each of the elements of the symmetry. And these are arbitrary coefficients for making different Hamiltonians. These are all the possible Hamiltonians that have C3 symmetry.
Professor Harter, real quick, it's rather faint, so I wanted to say it. Those balls, those masses are constrained to slide on those pins. It's really light gray, but you...
Yes, that is unfortunate. We use 2 light of cyan here. This is saying equilibrium 0 state, where all of those coordinates are the coordinates being how far out it goes on its little slider, and these have them all equal to 0. So the equilibrium position for this thing is presumably that where the coordinates are 0. So that's what that's trying to say. And then there are points here labeled by 0 mod 3, 1 mod 3, and 2 mod 3. So we're not a binary, but a trinary, I guess is what you would call the computer that would use this as its fundamental element. That's getting a little ahead of where our technology is right now. We really do everything with binaries. Even the quantum computers are all qubits binary. I think that we need to maybe expand that. There's probably possibilities for using more than just 2. And this is the first there. Now, the unit states associated with the position 0 mod 3, the position 1 mod 3, and the position state 2 mod 3 are being shown. So these are same as before. One mass out of place corresponds to a particular position state. Okay, and this is associated with particular power of the operator R that does 120-degree rotation here. And you have plus 120, you have minus 120, basically speaking. R to the minus 1 power is the same as R to the plus 2. That's a modular arithmetic for the base 3. Talk more about that in just a minute here. But I've written that here. 1 is the same as my R to the minus 2. That is, going this way is the same as going this way twice. And the same thing here. Going this way, positive, twice is the same as going this way once, negatively. Make sense? Lots of different notation that makes sense, so it sticks after a while. That's just a picture of where everything goes. So you're labeling the states by group operator. You're labeling what you can do to the states by group operators. The same, basically the same group operators. And then you're making Hamiltonians out of linear combinations of the operators. And the Hamiltonian actually does something, so those are do something operators there. So this is, the basic idea of how to use symmetry, whether it's classical or quantum mechanical. These could be quantum dots if we're moving some kind of wave function to be localized here, or here, or here. Those are our 3 states, and then we're going to make an eigenstate out of that. 3 eigenstates, actually. So, spectral decomposition, third roots of unity. That's the basic idea here, is that we've got 3 roots of unity. We're talking about a Hamiltonian that's made out of linear combinations of powers of these, and these things have a very simple Hamilton-Cayley equation. They have an equation that simply says r cubed equal 1. But you write that with a 0, r cubed minus 1, and the idea is to factor that. And the roots for it are the third roots of unity. And that's really a pretty easy thing to talk about. Basically, you're saying what is it that I can do to make a cube root of 1, basically. So in a complex plane, there would be something that pointed just to 1. But then there's something else that would be pointing to e to the 120 degree phase, and then there's something that's pointing to opposite. So these three numbers are the three third roots of unity that will resolve, and those are the actual roots of this Hamilton-Cayley equation. So there, for sure, is, if you want to know what the projection operators look like, one way to do it is just to say, I know that they're going to add up to 1. That's the completeness thing that we talked about when we talked about matrices. So we're guaranteed this particular equation. We're also guaranteed that if we multiply by r, then we'll get r on each of these, and they have their eigenvalues. Okay, so we're going to get this combination of the projection operators for r, and the same thing for r, really inverse, or square. You're going to square the eigenvalues for that. So this part of the thing, the spectral decomposition of this group, is trivial here, simply from the arguments that we know about what projection operators do. Then it's a question about turning that around, okay? Basically, you take those coefficients that are sitting there and you flip them, and you immediately get a thing where you have the projection operators in terms of the actual elements. So we essentially did a Hermitian conjugate of the matrices relating this to that to get the inverse. So it's really quite easy to find these projectors and their eigenvalues. This particular equation goes very well with the bra eigenvectors because the p is sitting off here to the left, and so the coefficients that we're talking about here, like that one or that one, which is right there, are easy to find. But this is the first step that's not quite so trivial to Fourier analysis. We now have Fourier analysis for a trinary system. And obviously we're going to take it to any n. Now, using this particular set of projection operators to make our character table, in other words, the coefficients that you see here are the coefficients for bras. We could write down the ones for the kits too. It would just be a transposed conjugate of this table. But we can also put phasors in here for each of these complex numbers. And here's where our p's for powers of the in the exponents, okay, or p for position, if we're talking about positions on that device that had 3 masses getting ready to do their thing. If I'm going to do transverse waves around that ring, I would probably like to have the real axis this way and the imaginary axis this way. And all the wave stuff that we'll talk about later on, I will do that. I will turn all the phasor coordinates so that the real axis points up and the imaginary axis points along a beam usually. So there's the first one, 1, 1, 1, 1, all pointing up. And then this one right here, well, same thing, pointing at 0 and then at 120. Actually, it's 120 squared, so it's minus 120. And then there's the plus 100. And there's the conjugate of that. You see where I have taken the imaginary and replaced it with its minus. Didn't affect this one because it didn't have any imaginary, but this one right here is minus that in this direction, the imaginary direction. Okay? So there's our version of a character table. Here's the thing you'd find in the libraries that might be exactly like that, or it might have a plus here and a minus here and vice versa down there. But these numbers that you do for these are golden. They apply to any threefold system that has C3 symmetry. And we have to make sure that we connect ourselves with a lattice. Okay, here it's circular, that's pretty obvious, but if you unroll it, you see there's going to be a certain length to the unit cell, if you will. I think we'll call that lattice length. It's 3 here. Okay, and there's a certain symmetry here. That's also 3. Okay, and then there's a lattice spacing A right here, and we have to say something about that. Basically, when you deal with this abstract sort of number theory, here's how you connect it to the actual lattice that has a length L and then some number n of atoms per that length. Okay, so the L has to be the product of the n, that's the symmetry, and the lattice spacing A, that is there. And then you can talk about wave vectors. That's 2 pi over a wave length, 2 pi times m over L, where m is the magnetic or wave momentum mode number. Okay, 3 things that begin with m. The original Zeeman splitting is due to a magnetic field, so these are called magnetic quantum numbers. But they're also mode numbers here. And then we're talking about k vectors. We're talking about momentum associated with the k vector. So m for momentum is fair game for mnemonics. See what I love mnemonics because I don't have good memory, right? Okay. Each quantum number follows a modular arithmetic. Sums and products are integers modulo 3. Okay, we have to define that a little better maybe. That is, they're either always 0, 1, and 2, or if you balance your band, you would like to have -1, 0, and +1. But you could go into the negative direction and have -2, -1, and 0, etc., depending on your choice of origin, really is what that amounts to. And modular arithmetic is found by just asking what do the exponential products give you here. I have a particular PM and I take it to a certain power P, talking about e to the I m 2 pi 3, one of the numbers that would be in this table. Okay, so I go ahead and put the power up there. I get MP times 2 pi over 3. This is 4 times 2. Okay, that's equal to just 1 times 2 with that extra 2 pi outside here, and that's of course equal to 1. So the whole idea of this is 2 times 2 mod 3 is usually not 4, but it's 4 mod 3. And that's the remainder after you divide 4 by 3 enough times. And this time we're going to divide it by once. But that's the idea of modular arithmetic. You're only allowed 0, 1, and 2 if that's the game we picked our origin, or if you picked it in the middle, you're only allowed -1, 0, and +1. Everything else is just the same. Now here's where you really put this to work, because here we're going to write a formula for the bands, the actual eigenvalues, in this case frequency, as a function of the m numbers, quantum numbers. And the way I'm doing that is fairly obvious, because each one of these guys has a e to the I m whatever the position point is. We've got a position point 0, 1, and 2 by our counting. And then I've got a certain m value right here, so I'm going to get e to the I m times p equals 0, 1, and 2. That multiplied by the 2 pi over 3 radian unit for the angular distance. So the eigenvalue of r to the p in m is just I e to the I m times p times our 2 pi divided by whatever the symmetry is. So each of these gets a coefficient like that. And that means then that the Hamiltonian boils down to this, and there's your band formula right there. Okay. Well, band formula consists of 3 eigenvalues, but 2 of them are degenerate, these 2. This is the one for 0, and then plus and minus 1 m values give you the same number, same cosine there. So the other way to write this is to take the Hamiltonian with, and now I'm assuming, this is a very special case here, where this parameter is equal to that parameter. That's most of the, if you take a typical solid state book, it'd be a long time before they start making those parameters do everything they can, and we'll get to that in a minute here. So we're going to get this for a band function, for a quantum Hamiltonian, for a classical phonon Hamiltonian. It's talking about vibrations, classical vibrations. Same vector, same kind of eigen value, okay? Same kind of matrix, just whatever those things are to go with this. Now, presumably some square of this would give that, but I'm not doing that right here. I'm just treating them as separate problems. But here is the deal. These are the +1, -1. Those are moving waves. And then there are standing waves that are made out of combinations of plus and minus, either a sum or a difference. That's equivalent to making sines and cosines out of these moving waves. These are all moving waves. Here I made them standing. That's called quenching. If something in the physics forces you into having things that have no complex numbers in them, that is, only real numbers, plus or minus numbers are allowed, but no complex numbers, that's a standing wave, that's a quenched wave. It's our C is gone, our C current is gone. It's just sitting there doing things out of phase or in phase, but nothing that's halfway between that. Anyway, remember that the K eigenfrequencies are the square root of they have a square root form to them. Vectors are the same, eigenvalues not. Because this thing right here is sort of the square of that. So whatever those numbers are, they have radicals around them. And that means, if you're talking about those kind of waves, here's a typical standing wave, a pattern, okay, a cosine, and then a sine, but those are the actual numbers that appear in it, 2, -1, -1, 2, -1, -1, and then 0, 1, -1, 0, 1, -1, for the 2 bands, one over here and one over here, and this is the actual frequency behind the scenes that is holding those numbers for this particular value of symmetry, 3. As we go to higher and higher values, we're going to start filling up all of those. And this is for the K matrix of a classical oscillation. The pictures, of course, are shown you right here. Those are standing wave modes, radial modes, just for this system, where it had to slide on the radius. If it's longitudinal, they'll look like that. Okay, now here's the power of the symmetry. Even with just 6 things, you discover that there's a lot of different Hamiltonians you can have. Most of them would just deal with this one. This would be called the block Hamiltonian. Okay, so it would have these r's off diagonal. the thing is, you've got to have this guy in order to have the cyclic symmetry. If you kill that, you get a completely different structure. Eigenvalues and eigenvectors are different if you kill that one. But every row and every column has got to have two R parameters. And then it will turn out that'll be the same thing for a situation where you hooked up the springs next nearest neighbors. Again, every row and column is going to have two of the springs. This one's weird. And you can see there's a halfway point out there, right there, where you put a T parameter for things that go next nearest neighbor. That means, in this case, that this one only couples to the one opposite side. So here's your Hamiltonian in terms of group operators. This Hamiltonian is just like the one we worked with. It has R and R inverse, and that's it. This one has R squared and the inverse of that, and then a 1. That's just a diagonal. That could be anything. And that's separate from the S. And then finally, this crazy thing that has R cubed and R minus cubed. R cubed and R minus cubed are the same. So whereas this one is going to, in order to make Hermitian Hamiltonian, require that this parameter right here be the complex conjugate of this parameter right here and this parameter right here. This one, of course, being conjugate opposite to it. This one being conjugate opposites. So if this is going to be a Hamiltonian preserves norm, then this parameter here has to be the star of that one. And same thing here. If you preserve the norm, then this parameter has to be the conjugate. So you have two kinds of parameters in there, this kind and this kind. But to make the generator Hermitian so that the unitary thing doesn't blow up, you need that. You end up with 1, 2, 3, 4, 5, and then diagonal 6 parameters altogether. That's as many parameters as this system can hold. So that's a good thing to know. Now, here are the character tables, which you find in a typical book on symmetry analysis. Here are the character tables for the six-fold symmetry. There's the actual waves with the transverse. The real axis is up here, imaginary axis is this way. Usually I designate that somewhere, but that's the way to do it. And then here is 1 mod 6. That's the mode of one wave modulo 6. Then the next one is 2 mod 6. 2 waves. Okay? And there's the imaginary part of that wave drawn there as well. Imagination precedes reality by 1/4. That sort of idea. And then here, this is the Brillouin band boundary right here. 3 and -3 are the same numbers. And so a wave that has 3 kinks, it only has phase positive, negative, positive, negative, positive, negative. Okay? And then, if I put 6 waves in there, I see 6 things behind the scenes there. Or, I'm sorry, 4 waves. This is 3 waves, 4 waves. I put 4 waves in there. 1, 2, 3, 4 waves in there. Or I put -2 waves in there, same modulo. And then this one's easy to see. 5 waves. I put 5 waves in. 1, 2, 3, 4, 5. Okay, that's the same as -1. That's the same as this one going backwards. You see that? See the one wave, but it's going backwards? Okay? It's the conjugate of this one. And then these two are conjugate. And this is self-conjugate. And you can see who's conjugate and not conjugate looking at this table. But this is telling you the physics over here, what you're talking about. You see? So these two are likely to be degenerate. And so are these two. and then this one's just by itself. It's on the band boundary, so there's only one of them. So all that complex stuff about band boundaries and things starts to make sense when you tackle the problem this way, using the symmetry analysis. And then here's this dispersion function that you would get in a quantum case. It would be the square root of this, which would be a straight line coming up here and ending there. That's the phonon band, which also gets quantized in solids, but it is a classical phenomenon, much more so than the tunneling model that we would be doing to actually get a dispersion like that. We're going to have a talk tomorrow by somebody that makes quantum dots of various geometries and studies their dynamics. So this is a connection to that. And the way you get the eigenvalues is really easy. You draw a hexagon and it's projection of the hexagon onto this. That's what you get when you just use the first parameter in what's called a block Hamiltonian. But block, there's no name I know of that goes with the next nearest neighbor Hamiltonian or the third neighbor Hamiltonian. All that happens is that this cosine wave gets to have two kinks to it. And then if you've got third nearest neighbors and that's all you've got, then you just have up, down, up, down. You just have three two-state systems hiding there. One of them down here, and then this is a third plus a doublet right there. So you get a very weird sort of dispersion. Now these dispersion functions don't have very many points. They have only 1, 2, 3, 4, 5, 6 points because we only have 6 symmetry. But if you go ahead and do 30 or something like that, then you'd have 10 points on each of these curves right here. And that's the way you build higher symmetry problems very easily from something that's a lower subsymmetry. Okay, now those 6 parameters could, some of them be complex. So if we have a first neighbor parameter here where r bar is equal to r star, it's possible for me to have a phase. I can have a complex parameter. That's certainly allowed. And then I would have to obey this law, but it just means I have plus or minus phi. This causes Zeeman spinning. The way you get the spectrum from that one is you take your hexagon and you rotate it by that phi number. That's the exponential of the parameter. Okay, and now you get Zeeman splitting. This is you can see this one right here is not is just fallen down a little bit from the top. That's second order motion of that eigenvalue, but this is close to first order motion right here. Okay, that occurred from what was degenerate before, but then split. It used to be like that. This one went up and that one went down, you see. And then the same thing with this doublet right here. It splits. So a C6 problem can have 6 non-degenerate eigenvalues. There have to be exactly as many eigensolutions and eigenvalues as you have parameters. So that's what's really neat about the symmetry analysis, is you don't just look at the block solution and there's some crazy other ones you have a foggy notion of. This one catalogs them all completely. Very tight ship. And this sort of thing can be applied to any of the high symmetry things. And it's just showing you some of those. Remember the character table, you should think of it in terms of the waves that are being plotted using phasors. If you just plot the waves and their imaginary parts, you get the background to the tables that I draw, where I have both the phasors and the waves behind there. Now, these things are quite big. I mean, you've got 16 things, you see, we're going to be going 0, 1, 2, 3, 4, 5, 6, and this is 16, so 7, 8. There's your Brillouin band boundary right there in the middle, more or less in the middle, right? They're just up, down, up, down, up, down, up, down. This guy right here is just one kink, k equal 1, for the whole lattice, okay? And this guy down here, 15, that's minus 1 modulo 16. Look at that. Same thing, except it's going backwards. And how do you tell what direction a wave goes? Remember that the phasor that leads gives. The phasor that lags takes. Every one of these has, this one right here is behind this one in time, okay? So it's being given by that one, if these phasors all go the usual way, clockwise, okay? Whereas this one is ahead of this one, right? So he's going to be giving, this guy's going to give to that guy and take from this one equally. So the wave will move in that direction without any of the phasors getting bigger or smaller. And the same thing's true on this one. That's 32, it's twice as big. 64, 100, 256. There's all little phasors in there. Just the color is the only thing it shows now. And remember that all of these have this formula: 2 pi I m mode number times power or position number divided by the n. That's all there is to this stuff. And therefore you've got what looks like a parabola, m and p, right? M times p equal a constant would be some color. There's your hyperbola, equilateral hyperbolas due to that, mp, for a particular color, right? Which is a particular phase. These are all things you can make on the web apps that we have. Now the rest of this, we're getting ahead of our time here, so I'm going to stop now, because the next thing that I'd really like to show you is the group theory of group velocity and phase velocity. That's a key thing for what we're going to end this course with, and that's a discussion of waves that gives you relativistic mechanics, and in the process quantum mechanics. But I point this out because that's basically what we're going to do. Now the simple structures that have stuff like that is fine. A quadratic dispersion is what we use in Schrodinger analysis. As soon as you get into a lattice, you realize that goes out the window, and you get, this is called the block dispersion, nearest neighbors only. And then this is the approximation. It makes a nice approximation in this neighborhood that's called Bohr dispersion. Omega equals ck squared, as opposed to omega equals some constant times the cosine of k. And these are the parameters that you need in order to make one of our systems into a Bohr dispersion. And then the rest of this is discussing the arithmetic of that leads to, well, first of all, beats. We've seen this already. We've talked about this. This is just fleshing it out a little bit, where I only have two side bands, that is, a zero frequency and then plus or minus 1. That's the situation with a C2 system. And there's a C3 system at work there, I believe. No, that's the C2 system, because I'm making this guy the same as this guy. So that's the Brillouin band coming around again there. And then this one is threefold, okay? And it does a similar beating if you maintain a degeneracy. So you can see the results of all of these adding up to make this. And then the rest of these, as we go to higher numbers, we actually start to make a wave that moves along and does some revivals. That's the generalization of beats. And as I say, I'm just sketching this. There's all sorts of neat stuff going on here that is described in the textbook. This one right here really shows it. As you go through this thing, you get all kinds of weird beats and things. The name for these patterns that form is coined by Joe Eberly at Rochester. It's called revivals. He wasn't looking at a system this simple. He was looking at an actual laser mode pumping system. When he discovered this behavior. This is where it really shows up. If I take a Bohr spectrum, just use a Bohr spectrum and let it go, I will be making patterns that you've seen already. That now sketch that very quickly here. It is a closed system with n things in a circle, just like our 3-fold, our 4-fold, or 5, 6, 256. But now it's essentially an infinite number. It's a continuum in time here, and then in angle here, and then time going this way. So wrap that up, that's what it looks like, and here's all these revivals occurring here. Now it's just 1 and -1 that you're worrying about here, and maybe a little 2 in there just to make it a little slightly interesting. You get the C2 beats. And then if you add something that has a delta M of 3, you can see the C3 and maybe a little bit of the C4 along with the C2 X, you see. But you get some stuff happening already there that's interesting. And then when you have 9 of them, wow, you can make a lot of arithmetic out of that. That arithmetic determines is associated with where these lines of different quantized slope cross. And they look a lot like our monster mash that we did in lecture 5. But you actually want to calculate where those things cross. Take 2 examples. Take 2 different denominators. A 1 over D1, multiples of that, or 1 over D2, multiples of that. See where they cross. That's a point that where you get some sort of reviving or revival behavior, okay? And where the time when that occurs is the Ferry sum of the 2 fractions, numerator over denominator plus numerator over denominator, but the plus signs are in separate numerator and denominator. That's the way a lot of your students add fractions, right? Well, now it's correct. Ferry is very much correct for figuring out what the time is. Then the sort of cross product, I call it the Ford cross. Ford has something to do with this long after Ferry. Ford's in the 1930s. Ferry is a geologist studying tides around 1815. So you're really talking a long time to get this stuff right. Anyway, this is the picture that Ford, well, he came up with a slightly different thing. This, I think, is simpler. But what we're going to do is look at all of the fractions we can with a given denominator between 0 and 1. So we first draw the circles that have the diameter of 1. And then we pick a certain numerator and a certain denominator. In this case, I picked this is the denominator axis, so I picked 2. This is 1/2, okay? And 1/2 points at 1/2, 0.5, okay? And then there's another one here that we had before. I thought I should have a half. This is just 1 over 1, okay? It's got numerator and denominator, and it, of course, points at 1.0. So we're off to the races here. The idea is that a Ferry sum is a sum of two of these fractions, okay? But it's a vector sum. That's what you're actually doing here. You're making a vector sum out of a factor of a sum of fractions in the Ferry form. So this vector, V2 here, that points at point 5, can be added to give us, you know, other fractions. Make linear combinations. This you make linear combinations of all fractions. Anyway, what you do is this is kind of weird. This vector actually points to this real value right here. Now we're going to make it point at other things. The Ferry sum of fraction is this vector sum, okay? And the idea of this construction is once you've done that, once you've got this thing, it'll intersect the old circle at some point. So you draw a line to where it meets the thing that's connected to that. In other words, you make a little triangle there out of that. And this points to a center of what is called a Ford circle. And it will turn out to be tangent to the top and the two sides. That's cool, okay? And this just, you keep up doing this and to make other things. Now, what I always remind people is a movie called The Titanic, in which there was a blue jewel being worn by the woman who was having her nude figure taken by her boyfriend, right? That's the jewel right there. Okay. So this lets you never forget this form of geometry, which is so important. Because the next step is, if she had more money, she would have had more jewels, and she would have filled up this part right here as well. You see, all of these things are gotten in the same way. And this is what makes the Ferry sum tree that you study quantum Hall effect, all kinds of things with this. We haven't really finished doing that yet, but I'm sure that it's possible and it's something we should do. Okay, so there's a whole bunch of fractions with denominators less than, well, we've got that up to 11 for those. So everything's going to be sort of filled in on that diagram right there with all of these numbers that are important, the ones that show up in those diagrams of the interfering waves. These are the super beats, or whatever you want to call them. And this is in a paper that we wrote just a couple of years ago, where you assign each of the fractions like 2/3 to two rectangles that are Thales rectangles in the circle that comes from that. That was one of our discoveries. So anyway, this is all stuff. The quantized Thales rectangles are part of an effort we're doing to make sense out of this type of stuff. So that's about it. I'm not going to go into the differential wave operators that you can construct by extending this. We'll just quit right here, and we'll be coming back on Coulomb orbits in the next lecture.